Thank you so much for giving me another chance to present
Yeah,
again. I'll try to move
yeah,
quicker than I normally do so we can
great.
keep our time. Yeah, I just want to introduce this is the toroidal shell electroacoustic transducer. My name is Divyamaan Sahoo, and this is also the subject of my master's thesis. So I'm on slide 2. Can you see slide 2? I just moved to slide 2. If somebody can confirm that I'm on slide 2. Um, Hello. Okay, I'm gonna move back to not full screen because I think this is gonna be better. So, just to probably people are familiar with what a toroid is. It's a donut, a bagel, the shape of a bagel, the shape of a donut. These are toroids, and they come in inductors. And I was very interested in the acoustic properties of toroids, and I'm studying a hollow shell toroid, so it's a hollow donut. I've done a literature search on these donuts and these toroids, and I saw in the 60s that some people had studied the electroacoustic solid toroids as free flooded ring transducers. And that's a basis for this work. And so I am more interested in the hollow shell electroacoustic toroids. So Fluge has covered the vibrations of hollow toroidal shells in his book, and I needed to obtain the equations for the stiffness, the equivalent stiffnesses, and the equivalent mass of the toroidal shell to get the natural resonances of the breathing modes of the toroid, both the hoop mode and the tube mode. So the hoop mode and the tube mode, you can see animations over here, but just to share what they are. So if you unfold the toroid, you get the cylinder, and it's basically the breathing mode of the cylinder, the extensional mode of the cylinder. That's a tube mode. That's what we're calling the tube mode. And the hoop mode is like a hula hoop. So the hula hoop mode is that the whole thing is expanding and contracting extensionally. So this slide, I'm on slide 4. I hope you can see the slides again, but I'm just going to assume that you are. And if not, please let me know. I'm using the energy method to model the hollow toroidal shell. And this work is following after Dr. Boris Aronov. Um, and I'm after all the equivalent circuit parameters here. And I have formulae for all of these, and this is definitely a work in progress here. So I'm modeling this as a vibration of two partial systems that are coupled, and this is after Gibby and Blechschmidt's excellent paper in 1933. So, to my knowledge, like piezoelectric toroidal shell transducers you don't really see them around. So, I wanted to build a prototype, had access, thankfully, to some cylinders. So there's this idea to make a segmented toroidal shell, which is inspired by these 90-degree elbow bends that you see in HVAC. They come in these cylinders and they're cut in this specific way. You can rotate these pieces to make 90-degree bends. You take 4 of these and you make a full toroidal circle. So that's the basic idea here. It's kind of like approximating a circle using a polygon. And so the slicing angle is half the interior angle of the polygon. So if you do a 20-piece polygon, you get a certain angle, and that's what we decided. So, it's really fun to map this out. It might sound easy, but it was an interesting challenge to, actually cut these pieces, put them together. And, I printed out a guide, actually did them with these cylinders. As you can see, the cylinder that we had was serially polarized, and that has some challenges, and we'll look at that later. So these are some more pictures of the fabrication process. I used a mini cutoff saw, coping saw with the diamond cord, sandpaper, machine coolant, the works. I was very, very grateful and privileged to get Austin Souza's fabrication guidance. He's an engineer at BTech Acoustics. I met him in the transducers class. I used more than 4 cylinders here, so measured twice and cut once is really the lesson learned over here. So it's really important for me to, because the cylinder was serially polarized, I had to make sure the polarizations were marked correctly when I was cutting them and assembling them. So each of these little rings, segments, I measured the polarization using oscilloscope, giving it a little squeeze, and you see this like waveform pattern, either negative, positive, so you know that it's you can confirm the polarization. Use the HP4194 impedance analyzer to measure the resonance, anti-resonance, then calculate the coupling coefficient. It chose the 20 of the best pieces that came about in this process. Had some extras, it chose the 20 best. And Austin drilled a hole through two of them, passed a ground wire, and then coated it in polyurethane so we could dip it underwater. So because these were serially polarized, you had to do something kind of odd to get them to vibrate uniform extension. You had to do a plus on the top, minus the bottom. It's a bit of a weird thing to do, but that's an artifact of these serial polarized cylinders. And so we were able to excite mode 0, the breathing modes, and mode 1 and higher modes. It's beyond the scope of this presentation. Again, use the HP4194 impedance analyzer to measure the resonance, anti-resonance in air. Did that in water, submersion underwater, noted the resonance, anti-resonance. And this is the exciting thing. We also measured the transmit pressure per volt, rotating in 1 degree steps, and comparing the two modes. So for higher order modes, like a mode 1 dipole mode, you see this really nice notch here if you're comparing it in these around 60 to 70, 60 to 80 kilohertz range. So this is what I calculated using the formula that I derived. This is what I measured. So you can see they're pretty close. And that too with the, modeling it as a single degree of freedom. So that's pretty cool. And the lower modes, the hunch is that it's flexural modes, so I'm kind of in investigation. And the applications for this would be for underwater acoustics and biomedical ultrasound. So thank you very much again for giving me this chance to present again. Sorry about the technical difficulties earlier. I'm very grateful to Professor Brown for taking me on, for mentoring me, and thank you. Thank you so much again.
Great. Thanks a lot, Divyamaan. Second time is the charm. Great. All right. So yeah, if anyone has any questions, please feel free to drop them in the Q&A.